So let me share.
Okay.
And it's here. Okay. Yeah, there is okay. So, hello to everyone. I am Mehran Maznani. First, I'd like to can you hear me appropriately?
Yes, Mehran. Okay.
Okay. I'm Mehran Maznani. First, I'd like to express my sincere gratitude to Stefania for inviting me to hold this session. And also I'd like to thank you, anyone who has attended this meeting or will watch it in the future offline. Today, I'd like to give a lecture very briefly about fractional and typical fuzzy inference systems and their role in systems control. So, as a starting point for our discussion, let me introduce you Mr. and Mrs. Smith. They have just got married. But this couple keep quarreling over looking at the universe and life, which has endangered their married life and can eventually lead them to this divorce. The problem is that Mrs. Smith says we should look at the life and universe by a wide lens, giving us a better understanding of the whole life. But Mr. Smith disagrees and says a narrow lens is better by which the life can be looked at in a close-up, precise form. So we should find a way to solve this problem and save their married life. Thus, let us see how they're looking at the universe. To figure it out, we shall make some modifications. So let's make some modifications, for example, some rotations and a cut between two lenses, and let us draw some lines. So, okay, now, so A, the lens of Mr. Smith is called a crisp set, and that of Mr. Smith is called a fuzzy set. The universal discourse may be the real line. A crisp set is characterized by a membership function mapping the domain into only two values, 0 and 1. Thus, the membership function of a crisp set assumes only two values, 0 and 1. That's why it sharply drops from 1 to 0. However, in a fuzzy set, the transition from membership to non-membership is gradual rather than abrupt, and the membership function maps the domain into a subset of the interval 0 and 1. One of the important concepts in fuzzy set theory is that of linguistic variables. For example, I'm working in a city located in the south of China, and its weather is semi-tropical. So now here is very warm and a little hot. But I think the temperature in Tartu at the moment may be cold. These sentences can be realized when people are talking. So how can a machine understand these sentences? It turns out that the concept of linguistic variables and linguistic values with some rules coming from fuzzy set theory play the role of a translator between a human and a machine, such that a machine can understand what we mean by, for example, a tall boy, a hot coffee, a very cold day, and so forth. More specifically, a linguistic variable is a variable whose values are fuzzy sets. For example, height is a linguistic variable, some of whose values are short, medium, tall, while hot, warm, cold exemplify the values of the linguistic variable temperature. Since the concepts of a fuzzy set and a linguistic variable are very important, I recall them briefly here. So let's start the main subject, fuzzy control systems or fuzzy logic control, or sometimes it's called fuzzy inference systems, but an FIS is not always an FLC. If an FIS is employed for the control of a system, then its role is the same as an FLC. There are two main approaches for the design of a fuzzy controller. One of them is based on fuzzy if-then rules, and the other is on the basis on fuzzy mathematics. In the fuzzy mathematics approach, the mathematical model of the system needs to be known. In this approach, the uncertain conditions, parameters, and or functions are considered as a class of fuzzy sets, which are mainly fuzzy numbers and or fuzzy functions. In this approach, finding the fuzzy controller deals with fuzzy differential equations, fuzzy integral differential equations, fuzzy calculus, and fuzzy algebra. And more concretely, the control theories are developed in the context of fuzzy mathematics. Our last paper has been published yesterday, which is about a review on fuzzy differential equations. And those who would like to know more about fuzzy differential equations and make yourself up to date, reading this paper is recommended. Actually, this paper at the moment maybe not found by search in Google, because it's in the stage of early access. So you can go through the website IEEE Explore and search the title of the paper, and you can find it, this paper, easily. And this paper is open access, so it's simply at your disposal. And we have reviewed the topic of fuzzy differential equations in various aspects, their solutions, their method, the method of solutions. So many approaches that have been dealing with fuzzy differential equations, the challenge, the future, perspective, and so other things, their applications, the control applications, and so many other things. So let's continue our topic. The approach in which fuzzy if-then rules are involved is divided into categories. Those which are based on interpolative reasoning, for example, Mamdani's fuzzy inference system, and the other is related to the structure that's called Takagi-Sugeno architecture, or TS model, or TS architecture, or TS model. In TS model, the dependency of Y on X is indicated by a crisp function with a truth degree of the fired or activated rule. This method is almost always used when a model of the system is known. If the model of the system is known in a closed mathematical form, for example, by a nonlinear differential equation, this approach enables us to represent the model of the nonlinear system in the form of a bunch of fuzzy if-then rules, where each consequent part includes a system of linear differential equations, which shows a local behavior of the system approximately. Thus, analyzing the system and designing a controller for a nonlinear system may be done by the use of linear control theory. And in this way, we deal with linear matrix inequality problems, parallel distributed compensator approach, and so forth. If the model of system in a closed form is unknown, but the input-output data set of the system is available, then this approach may also be used. In this situation, designing a controller may deal with some machine learning methods, such as the so-called adaptive neural network fuzzy inference systems, ANFIS for short, or genetic algorithms, particle swarm optimization algorithms, and so on. Perhaps the most popular and important approach which have had a profound impact on recognizing fuzzy set theory as a powerful tool in the applications has been and continues to be the interpolative reasoning. In such reasoning, fuzzy if-then rules are employed for the description of the system behavior or the way in which a system can be controlled. The fuzzy if-then rules here describe the dependency of Y on X by the Cartesian product of the fuzzy sets in the antecedent and consequent part. So both A and B are fuzzy sets. X and Y play the role of linguistic variables for which A and B are linguistic values. There are two types of interpolative reasoning. The typical one is called typical or first order fuzzy inference system. And the other, that is a new generation of interpolative reasoning, is called fractional fuzzy inference system. Such fuzzy inference systems can be used in situations where the model of a dynamical system is known or unknown. I mean, these FISs are either model-based or model-free approaches. If a mathematical model of the system is known, then employing these FISs involves experts' knowledge, learning methods, or optimization methods. And if a mathematical model of the system is unknown or is not available, then for applying such fuzzy inference systems, we need to use either expert knowledge or some information about boundaries of the input and outputs of the system. As a result, by the aid of these fuzzy inference systems, so many control systems can be designed, among which are those where fuzzy inference systems operate as an independent and single controller, or FISs, whose inputs are the error or the derivative of error and or the integral of the error, which are called PID type fuzzy inference systems. The other controller is fuzzy PID, where fuzzy inference systems are applied for the manipulation of or adjusting the gains of a PID controller. And there are also so many other types of fuzzy controllers that are defined based on interpolative reasoning approach in combination with the other controllers. For example, the combination of the sliding mode controller with the mentioned FISs makes a controller that is called fuzzy sliding mode controller, and so forth. So as you see, the area of fuzzy controllers is very wide with a high variety. Thus, here we shall focus on one of the general ways for the design of a fuzzy controller. The fuzzy controller that has been selected to be explained underlies the interpolative reasoning. The approach is model-free with some information about the boundaries of inputs and outputs of the system, and eventually a class of PID type fuzzy controller is designed. Before starting the design of a fuzzy controller, some points should be expressed regarding the control system. There is a system, a dynamical system, that sometimes it is called the plant. Our goal is that the plant exhibits certain desired characteristics or behavior. The desired behavior here is assumed to be tracking the reference denoted by R. For achieving the goal, we need a controller. The controller needs to have a sense of the output of the plant. Such a sense is provided by the error signal or error function, that is the difference between the output of the plant and the reference. Since both the error and its derivative have been considered as the inputs to the fuzzy inference system, then the fuzzy controller is called PD type fuzzy controller. If we also consider the integral of the error as the input of fuzzy inference system, then the fuzzy controller would be called PID type FIS. Sometimes even PD type FIS is also called PID type FIS. It should be noted that if we use fuzzy inference systems in the of the type of fractional fuzzy inference systems, so PD type fuzzy controller is called PD type fractional fuzzy inference system. So we have a closed loop system, including a plant and a controller. We have assumed that the model of plant is not available. The plant should be controlled by a controller. The controller consists of a fuzzy inference system with 2 inputs and 1 output. The FIS is of the type of interpolative reasoning, so includes fuzzy if-then rules, which determine the dependency of the output on the inputs. It should be noted that the procedure of designing the controller for the typical and fractional fuzzy inference systems is almost the same. I will point out whenever there is any differences. For the sake of simplicity here, we consider a set point, a constant, as the reference should be tracked. For example, it may be the unit step. The unit step is indeed important because if a system has a satisfactory step response, then it is expected it has also a satisfactory response to the other references. The reason is that almost any function can be well approximated by a combination of step functions. So in order to construct the controller, we should first characterize the fuzzy if-then rules. The model of the system is not available, but it is not hard to determine the boundaries of the input and output of the system. Suppose that the minimum and maximum values of the output are y sub min and y sub max, the output of the plant. So the boundaries of the error can be also obtained as E sub min and E sub max. Based on these values, we can consider a number of membership functions covering the interval E sub min and E sub max. That which type of membership function or how many membership functions should be considered are not discussed here, but usually 7 to 5 numbers of triangular or trapezoidal membership functions are considered. Next, we can also label these fuzzy sets to be recognized better. For example, PB means positive big, Z means near zero, NS means negative small, and so on. Actually, in this way, we clarify the fact that the error is considered as a linguistic variable whose values are NB, NS, Z, and so forth. What should be pointed is that the boundaries of the output may not be necessarily the maximum and minimum values of the output of the plant. They may be the boundaries of an interval of the output in which we would like the controller operates or is active. For example, this is an inverted pendulum system, and this is a sensor by which the pendulum angle from the vertical axis is measured. Thus, the output of the system comes from this sensor. If we would like to control the inverted pendulum for an interval of the deviation of the pendulum from the vertical axis, so this interval determines the maximum and minimum values of the output of the system. I mean y sub min and y sub max. For example, if we would like to control the system when the deviation of the pendulum from the vertical axis is in the interval plus and minus 1 radian, then the boundaries of this interval that are plus and minus 1 are considered for the maximum and minimum values of the output. And since in the vertical position, the angle of pendulum is 0, and our goal of control is to keep the pendulum upright, then the reference is set to 0. Here you can see some of the membership functions of the error considered for the control of inverted pendulum system. Similarly, the boundaries of the derivative of error can be found based on the information about the relative changes of the output. Here, y sub k plus 1 and y sub k are two samples of the output whose differences may be considered as an approximation of the derivative of the output, is which an approximation of the boundaries of the derivative of error can be found. Note that we don't need to find the exact value of derivative of output. Its approximation is also okay. And we can consider some of the sets as the values of the input of the plant, or that is equivalent to the control signal, and label them. In the case of inverted pendulum system, we can find out the maximum and minimum voltage of this motor, based on which some fuzzy sets can be considered. The voltage, the maximum and minimum voltage of this motor is also the maximum and minimum value of the control signal, or the input to the plant. So till now, what have done is that we considered error, its derivative, and the control signal, I mean the input to the plant, as linguistic variables whose values are fuzzy sets, which have been determined and labeled as PB, PS, Z, and so forth. Now we need to fill out the table that is another representation of fuzzy if-then rules. In other words, we need to determine the value of the linguistic variable in the consequent part of each rule. the value of the linguistic variable u of t in each row. First, for the sake of simplicity, we assume that if u is positive, then y is also positive. And if u is negative, then y is negative. Positive input leads to a positive output, and negative input produces a negative output, just for the sake of simplicity. So we already know the minimum and maximum values of y sub min and y sub max. Without losing generality, we assume that the minimum value of y is 0 and the maximum value is somewhere, for example, here greater than r. Thus, according to this relation, the horizontal axis stands for the maximum value of error, and any point on this line corresponds to the minimum value of error, E sub min. Therefore, clearly, if the output of the plant is near the horizontal axis, it means that the error is positive big. Near this line, it shows that the value of the error is negative big, and near the reference, it stands for the value of the error is z or near 0, and so forth for the other values. So based on what has been already explained and the assumptions, if the output of the plant is near here in the circle, near here in the circle, so the error is positive big, and if the slope of y, or the change in the output, is very small, near 0, then based on this relation, the derivative of error is also near 0. In this situation, the controller with a high value should move the output towards the reference in order to have a fast response and a small rise time. If the output of the plant is in this circle, near this area, so the error is still positive big, and if the slope is positive small, then the derivative of error, according to that relation I mentioned, is negative small. In this situation, the controller should still push the output, but since the derivative of the output is positive small, then the control signal does not need to be big. So a positive small value is enough. And let me go to the other situation. In this situation, the output is approaching the reference with a high slope. This situation may be viewed as when you are driving a car with a high speed and you are very near the destination or final point. So what do? You naturally press the brake gradually. The similar thing happens here. So the control signal should be negative small. We may also consider a negative big value for the control signal, but such a choice, negative big, maybe does not let the output reaches the reference. As you may have recognized, characterizing the fuzzy if-then rules is to some extent heuristic and depending on the problem. So I should pass the other situation, and if you continue in this way, eventually you may obtain a table like this one. There are some points that should be mentioned here. We implicitly assume that the system is controllable and observable. Meanwhile, the fuzzy if-then rules represented in this table is not unique, and it may change based on your opinion or preference in the design of controller depending on the problem. But such fuzzy if-then rules shown in the table is often used in literature and applications. Thus, now the fuzzy rules have been determined. Then rules block is known. The fuzzification method depends on the problem, but usually is singleton because of the simplicity in the computation. The defuzzification is also usually the center of gravity. Thus, so far, everything between the typical fuzzy inference system and the fractional fuzzy inference system is the same. The difference between these two FISs comes from the inference block. So now you know how to design a PID type fuzzy controller for a plant whose model is not available or unknown. In the next slides, we will see some applications of this structure. But we shall first give a brief explanation about typical fuzzy inference system, particularly Mamdani's FIS. So the question is, what is a fuzzy inference system? A fuzzy inference system, in a broad sense, is a reasoning system for the explicitation of fuzzy constraints on the variables whose constraints are implicit in a system of fuzzy assignment equations. For example, here, the fuzzy constraint on X is A, and it is explicit, but the fuzzy constraint on Y is implicit in R. So FIS outputs the fuzzy constraint on Y, and actually it explicitates the fuzzy constraint on Y. The reasoning mechanism is often that of composition rule of inference. A fuzzy inference system, in a narrow sense, which has been used and applied in so many applications, corresponds to the interpolative reasoning. In such a fuzzy inference system, the relation between the variables is presented in the form of fuzzy if-then rules, and a fuzzy if-then rule is translated by the Cartesian product of fuzzy sets A and B. And in the presence of a minor premise, here it is the input X is X not 0, the translation of the system is a joint constraint on X and Y in this form, in which if the base operator is considered as minimum operator, then fuzzy inference system is that of Mamdani's approach. This slide shows the inferred result of Mamdani's FIS for a single rule. If there is a set of fuzzy if-then rules, then the output often is obtained by disjunction of the rules, and using a defuzzification, crisp output is obtained. As a result of this part, let's apply the fuzzy controller on the nonlinear inverted pendulum system. The defuzzification method is the center of gravity. The fuzzifier is singleton. And the defuzzifier is COG, where the rules are known, and the inference is that of Mamdani's approach. And the aim is to keep the pendulum upright, so the reference is set to 0. The initial condition has been considered as 0.5 in radian, and as you see, the fuzzy controller could well stabilize the pendulum. There have been some reasons for presenting such an approach for designing a fuzzy controller, and also there are some reasons for choosing the inverted pendulum system. Actually, the inverted pendulum system has some important applications, among which are in self-balancing robots, in a Segway, in earthquake-proof building, and so forth. Oh, sorry, I think in this Segway, the fuzzy controller has not been employed. Yes. So in so many applications, for example, in Segway or self-balancing robots, the model of system is not available, or obtaining such a model is very complex. Meanwhile, in so many cases, the mathematical model of the system does not present the exact behavior of the system. So the value and importance of fuzzy inference system-based approaches for designing a controller, which does not depend on the model of system, becomes more apparent. In the examples that have been mentioned, the fuzzy controller serves as a means of stabilizer, the role that has been played by such a controller in so many other applications. Here, I would like to explain briefly one of them. Note that in the case of inverted pendulum system, the fuzzy controller has been used for the stabilization of the pendulum. In other words, the pendulum was vibrating around the vertical axis, and fuzzy controller is used to reduce the vibration, and eventually it stabilizes the pendulum on the vertical axis. Similar thing happens in a camera. When we want to take a photo or record a video with our mobile phone or a camera, for example, there might be some vibrations and shakes. In this situation, how can we obtain the model of such a system for which a fuzzy controller should be designed? A fuzzy inference system might be used and actually has been used for the stabilization of the video that is being recorded. In this case, the object that should be stabilized is the video or photo that is recorded or taken. And we may consider the error as the displacement change in pixels in a direction, and the rate of such a change is considered as a derivative of error, and the control output may be some modifications in the position of a particular lens that is called lens stabilization, or in a particular sensor that is called sensor stabilization. For example, here we can consider the vibration that happens when sorry, the vibration that happens when we are recording a video and we are running or walking. So when this slide shows the first application of fuzzy logic in the stabilization of the video being recorded by a camera. I think it has been applied about 30 years ago, and the company that produced this camera, I think it's Matsushita, a Japanese company. And now the stabilizer is off, and now yes, it shows the difference between, and now the stabilizer is on in the left hand, on your left hand you can see the performance of the stabilizer when it is on, and this is a fuzzy systems that stabilize the video that is being recorded, and in the right hand side the stabilizer is off. So I apologize you. So, and now after 30 years, we have stabilizers that do their task more effective than before. Actually, fuzzy inference systems are used in so many applications. Let me show you the stabilizers that now are used in the new cameras in these days, and they have been used in in our mobile phone. But the point that I want to mention is that fuzzy inference systems even now are used in so many camera for the stabilization and enhancing the quality of image, and in so many other consuming products. But some companies don't reveal the methods that have been used in their products, and only few of them do that. If you hear something about intelligent dynamic noise cancellation, active noise cancelling, active stabilization, or super steady feature in camera, or intelligent control in consuming products like washing machine. So possibly with high probability they use fuzzy logic. So let me show you some other examples. Samsung is one of the companies that that use fuzzy systems in their products, in washing machine and in other products, I think. And the arrow shows those rice cookers in which fuzzy systems have been applied. The 3 rice cookers in the top of the list have been used fuzzy systems as the fuzzy controller. And this rice cooker is a product of Philips company. Here, this rice cooker with fuzzy logic technology and so forth. There are also so many other examples of the applications of branches of fuzzy logic, particularly those in which fuzzy inference systems have been employed that I pass. Hereafter, I shall start introducing a system that enables us to construct models mimicking the way in which we think and reason. That's why we call it a new generation of fuzzy inference systems. The fractional fuzzy inference systems were introduced in 2020, last year, actually after 45 years since the typical fuzzy inference systems were introduced, practically in 1975. This is the first time that a new generation of fuzzy inference systems is presented, which not only outperforms all the typical fuzzy inference systems, but also includes them as a very special case. Here we shall focus our attention only on those aspects of the concepts which have a direct bearing on the subject of this seminar. So for more details, please refer to the original paper. Fortunately, the paper is open access, so it is simply at your disposal. Assume we are given a system that needs to be controlled or modeled. And we are gonna use fuzzy inference system for controlling or modeling the system. In order to get the best output or the optimal output, we have applied all the learning algorithms, all the optimization algorithms, improving techniques, and all alternatives for improving and getting a better result or the optimal result. But we concluded that there is no way to obtain more satisfactory results. And we still or our, for example, our boss need a better result, or we still ourselves need a better result. So what should we do? One may suggest us to increase the type of FIS. Actually, this is the alternative that happens now in the literature, increasing the type 1 fuzzy inference system to type 2 fuzzy inference system. However, increasing the type of fuzzy inference systems come with some challenge. We need to make some change in the antecedent and consequent parts by employing type 2 membership functions. Such an FIS comes with computational complexity. Meanwhile, the inference block needs to be changed and adapted with the type 2 fuzzy inference system. And moreover, an additional term or block needs to be considered and added to the system structure for reducing the type of inferred fuzzy set, I mean the type reduction block. But if we are familiar with fractional fuzzy inference system, then we can well put another effective alternative on the table and say, don't increase the type of FIS, use the fractional fuzzy inference system. One of the advantages of such an alternative is that only the inference engine needs to be changed, and indeed slightly. And the other units and the other units remain without any change. Assume there is a fridge or camera, washing machine, or any software or hardware system in which a fuzzy inference system has been employed. So if we want to improve the performance of these systems, we only need to change the inference block. The way of thinking that machine based on which reason and produces the output. So only this block needs to be changed. And it turns out that independent of the problem in question, a typical fuzzy inference system never leads to results which are more satisfactory than those obtained by the fractional fuzzy inference system corresponding to the typical fuzzy inference system. There are two theorems in our paper that have been proved, and you can refer to those. In fact, what has been presented in our paper is type 1 fractional fuzzy inference system. In a similar way, we can generate type 2 fractional fuzzy inference systems. So in this perspective, fuzzy inference systems may be categorized as the typical or first order and fractional order fuzzy inference systems. So we have first order type 1 fuzzy inference system, first order type 2 fuzzy inference system, and in the fractional side, we have type 1 fractional fuzzy inference system, type 2 fractional fuzzy inference system, and so forth. Actually, we have elaborated on and developed fractional fuzzy inference systems of type 2 and demonstrated that type 2 fractional fuzzy inference systems come with many practically new concepts. You may know so far, first order or typical type 2 fuzzy inference systems have come with 3 concepts since around more than 20 years. However, in our upcoming paper, we have demonstrated that type 2 fractional fuzzy inference systems comes with more than 12 new concepts. Eventually, it turns out that fractional fuzzy inference systems are able to dominate over first order or typical fuzzy inference systems. On the basis of aforementioned explanations, so the applications of fractional fuzzy inference systems cover all the area in which typical fuzzy inference systems have already applied and yet beyond them. Some of the potential applications of FFIS, to name but a few, is in control systems and automation, fuzzy control systems, fuzzy sliding mode control. For example, we may combine sliding mode control with fractional fuzzy inference systems. PID, we use fractional fuzzy inference system for adjusting the gains of the controller in the scheduling plan. We can try to design PID type fractional fuzzy inference systems. And we can use FFIS in image processing. So the cameras in which now they have been employed typical fuzzy inference systems for the stabilization, for stabilizing the video. So if they change or replace the typical fuzzy inference system with the fractional fuzzy inference system, the performance and the quality of their camera will certainly improve. In data mining and prediction, there are so many papers that have been published, and so many applications have been proposed and applied, and in data mining and prediction based on typical fuzzy inference systems. So if you apply fractional fuzzy inference, for example, in financial time series forecasting, you will certainly get better results. In combination with other methods, for example, in the next slide, you will be familiar with the fraction can be trained by, for example, convolutional neural networks. And in fuzzy clustering and classification, the clustering and classification will be improved if you use fractional fuzzy inference system instead of the typical fuzzy inference system. Actually, perhaps more than 10,000 papers, or maybe 2,000 papers and books with applications and a variety of subjects have been presented based on typical fuzzy inference systems. If you take each of them, you can get more satisfactory result than that obtained in those papers by applying fractional fuzzy inference systems in place of typical fuzzy inference systems. For example, you can easily search what have been done by the use of Mamdani's FIS. So you can certainly improve it by applying FFIS instead of Mamdani's FIS. Let me show you an example. For example, assume the topic of your research is agri-food supply chains. There are some approaches in agri-food supply chains which have been applied based on a typical FIS. So you can get better result by applying FFIS. Or for example, if Philips or Samsung, Panasonic, and the other companies apply FFIS instead of the typical FIS in their products, they can be sure that the quality of their products increases more than before. I mean, the performance of the stabilizer, for example, in camera or mobile phone increases, the quality of image. The electricity consumption in electrical consuming products decreases. There are a lot to say, but I prefer to pass. One of the points that I wanted to highlight is that FFISs make it possible for us to cooperate with high-level companies or define a project such that we can be sure that the final result is more satisfactory than the result which is at disposal right now. I'll try to finish my lecture very soon by presenting a brief introduction of FFISs conceptually without giving technical details. In our daily life, we almost always make a decision based on a relation between the quality or value and quantity or volume that is implicit or explicit in our goal or the task we are going to do. For example, the volume of a book, magazine, or an article is read based on its value. We read the volume of the pages of the book as much as the value of the book or the information included in the book. The amount or volume of budget that is invested in a project is related to the value of the project, and so forth. As a starting point for our discussion, it is convenient to consider a fuzzy set as a granule of information. Such a viewpoint directs us to consider not only the value, but also the volume of information included in the fuzzy set. Viewed in this perspective, the relation between the value or quality and the volume or quantity of the information plays a major role in making a decision based on given information. In the subject of fractional fuzzy inference systems, the volume of information is related to an index, which is called the fractional index. And value of information is related to the truth degree coming from the antecedent part of a fuzzy if-then rule. As already mentioned, in everyday decision-making, we almost always consider a relation between the value and volume of the subject for which we make a decision. For example, the volume of a book is read based on its value. We read the volume of the pages of the book as much as the value of the book or the information included in the book. This slide shows the relation between the value and volume that is considered as a monotone function, the model of relation that often we consider in our mind for making a decision. This is also the case for watching a movie or listen to a lecture. The more time we spend on a speech, the more valuable it is. It should be noted that a membership function that is called a fractional membership function, if there is a relation between the value and volume of information, when the membership function is in active mode. For example, this membership function is a fractional membership function because there is a relation between the value and volume in this membership function. A fractional index can be considered as a function ranging over the interval 0 and 1. This property completely makes a direct connection between the value or quality and the volume or quantity of the information. More importantly, if the function is a monotonically increasing function, then by an FFIS, we can state that the more valuable the information, the more significant the volume of information that is involved in the process of making a conclusion. In other words, increase the quantity if the quality is high, decrease the quantity if the quality is low. So an FFIS intelligently considers not only the value of information, but also the volume of the information included in fuzzy rule base for making a conclusion. As the other example, let's take a look at the propagation and report of news in media. In everyday life, we receive a lot of news and information from radio, television, newspapers, and generally from media. This news conveys information. The value of news is related directly to the value of information conveyed by the news. The value of news or information has a major role in determining the volume of news that should be propagated and the amount of time that should be devoted to the report of the news. For example, assume an event happened in a city. The news of this event is reported by media. If the value of this news is not high, I mean the news is not very important, then naturally the news is propagated or broadcast with the low volume, and it may be limited to the border of a country or maybe only some neighbor provinces. In the case the value of news is high, the volume of news or information propagated by media increases, such that it may be reported by the media in some other countries. If the information included in the news is very important, then the volume of information and news propagated by media becomes very high. So naturally, as it happens in our daily life, there is a relation between the value and volume of information. Now consider the case in which there is not an effective relation between the value and volume of information. In other words, what would happen if there wasn't an effective relation between the value and volume of information in our world? In this status, in the case of news, the media in the world, in all television, websites, radios, and so forth, continuously was reporting news no matter its value is high or low. The news that wasn't important would be reported in all media, and the high value news would be also reported by all media. In the case of reading a book, it's interesting. In the case of reading a book, if the value of the book was low, so we had to read all the pages of the book. But fortunately, our mind naturally makes an effective relation between the value and the volume of our goal. So the principle of the mechanism of inference in FFISs is the exploitation or the maximum exploitation of the information by considering a relation between the value or quality and the volume or quantity of the information. What should be understood is that the common principle of fuzzy set theory, fuzzy inference systems, is to enable us to make a mathematical model that reflects the way in which human thinks, make a decision, and compute based on his perception. In this direction, basically, fractional fuzzy inference systems derive their inspiration from the informal ways in which humans make a relation between the value and volume of imprecise information for their rational decisions. Now, we shall turn our attention to the fuzzy inference systems. How does a typical fuzzy inference system work? Let's recall it. Consider the single fuzzy if-then rule, Fx is X is A, then Y is B. With the crisp input, X is X naught. The figure in the current slide shows visually the output fuzzy set highlighted by the green color. As is seen, the output of fuzzy set is obtained only based on the consequent part membership function cleaved by the truth degree of the antecedent part. The obtained fuzzy set includes information. The value of this information determined by the level of the truth degree coming from the antecedent part. An increase in the truth degree makes an increase in the value of the information extracted from the membership function B. As the truth degree decreases, it may be postulated that the value of the output information decreases. So, as you see in a typical fuzzy inference system, only the value of information changes by clipping the membership function of the consequent part, but the volume of information does not. So, in typical fuzzy inference systems, maximum volume of information is exploited for making a decision. There is no relation between the value and volume of the information in the process of making a conclusion. The behavior of typical fuzzy inference systems is similar to the status of media in which no relation between the value and volume of information is considered. So it means that no matter whether the news conveys low or high value of information, it should be propagated with the maximum volume. However, for making an intelligent decision, not only the value, but also the volume of information should be considered. Here, I'd like to show you a simple comparison between the typical and fractional fuzzy inference systems in cases that may happen in our life. In the case of this couple, perhaps the lady may change the channel, but the man disagrees and says, let's watch it through. It's not bad. But the lady says, I watch the program as long as I find it is worthy of enough. So the lady's behavior in reasoning might be viewed similar to the reasoning mechanism of a fractional fuzzy inference system. In the second case, the man continuously is watching a program and says, if the film doesn't lack the value, I watch it through. If the film doesn't lack the value, I watch it through. The lady says, turn it off. Don't waste your time. Here, that man's behavior in reasoning might be viewed similar to the reasoning mechanism of a typical fuzzy inference system. One of the key points is as a fractional indices or the order of a fractional fuzzy inference system approaches one, or as the fractional, all the fractional indices assume unity, then the fractional fuzzy inference systems are reduced to typical fuzzy inference systems. So the typical fuzzy inference systems are very special case of fractional fuzzy inference systems. And as I mentioned before, the fractional indices can be in the form of a function of the truth degrees, and they are called functional fractional indices. This slide shows some functional fractional indices, and for example, when there is a simple linear relation between the fractional indices and the truth degree, it means that there is a linear relation between the value and volume of information. There is a quadratic relation between the quality and quantity in the processing of information. This slide shows a comparison between the Mamdon's FIS and the fractional fuzzy inference systems for a single input and single output with two rules. These are the consequent parts, and mu sub 1 star means the truth degree is coming from the coming from the antecedent part in the first rule, and mu sub 2 is the truth degrees that coming from the antecedent part in the second rule. And in the next slide, we would like to show the output of fuzzy sets of these two FISs for these two rules by varying the truth degrees of the antecedent parts. And we assume that the membership functions, the membership functions in for example, the membership functions in the antecedent part, they are in a half overlap. And for example, if this is the mu star 2, and this is, for example, 0.2. So here we have, for example, for example, until here, from here until here, in this period, we want to our simulation covers these sections when there is such a relation between the truth degrees in coming from the antecedent part. And we considered the relation between the quality and quantity as a linear relation. So as you see, for example, here, the truth degree is 0.5, 0.1, and a huge volume of this membership function is cooperating in the consequent part in the infrared fuzzy set. But here the volume of information is based on the truth degree. Let's start. And as you see here, the output of FFIS is a fraction part of the output of the typical FIS. And the behavior of the typical FIS, for example, in Mamdon's FIS, is almost always like an up and down. But in FFIS, based on the relation we consider for the between the volume and between the value and volume of information, actually based on the function that we considered for the fractional indices, the behavior is different. So a high variety of different behaviors we can have in the output of the FFIS. One of the features of information is its direction. This feature emerges in the direction of a fractional index. So corresponding each typical membership function, there are two forms of fractional membership functions called as alpha and beta forms, and indicated by an arrow on the top of the label of the fuzzy set. For example, this is a fuzzy set. Its name is positive big, and this arrow from right to left indicates that this is a fractional membership function, and it is of the type of beta. And similarly, this arrow shows that this is the membership function of the fuzzy set labeled as PB is a fractional membership function of the type of alpha. So by the aid of these two forms of fractional membership functions, FFISs with different modes can be considered. And if you consider these membership functions as a set of membership functions in the consequent parts of a fuzzy inference system, so for example, we may consider the PB as a fractional membership function. And we have a fractional fuzzy inference system, and this is another fractional fuzzy inference system because this membership function is in the alpha form. This membership function is in beta form. And so for each membership functions, we have two options in alpha form and beta form. So we may consider so many modes of fractional fuzzy inference systems, and eventually it turns out that corresponding to a typical fuzzy inference system, where the consequent part of the rule base consists of m membership function, there are possibly 2 to the power of m modes of FFISs. Thus the degree of freedom in the design of fuzzy systems and the application of FFIS increase significantly. In addition, it should be noted that for each mode, each fractional index can be considered as a function whose range is the interval 0 and 1, or a subset of the interval 0 and 1. And so the alternatives for considering such a function is very high. Among the different modes of FFISs, there is a mode which is more interesting and yet important, that is called aggressive mode. This combination is very helpful, particularly in the control system application. Actually, it makes it possible to have a control system that reacts faster than the typical FIS. For more details, please refer to the original paper. There are also some other features and concepts coming with FFISs, among which the fracture index and the left and right order of a fuzzy inference system are very important. Based on these concepts, the typical fuzzy inference systems are defined as the first order FISs. In other words, they are from first order. However, FFISs are fuzzy inference systems which are from fractional order. If you are familiar with fractional calculus, you know that the fractional derivative of a function approaches the integer order or the first order derivative of the function as the order of the fractional derivative approaches 1. Similarly, in the fractional fuzzy inference system, as the order of the fractional fuzzy inference system approaches 1, the behavior and the output of fractional fuzzy inference system approaches the typical fuzzy inference system. For example, here, this is the output of the controlling of a inverted pendulum system by the fractional fuzzy inference system in some modes. There are some modes of fractional fuzzy inference systems, and as you see, this arrow shows the direction of the order of fractional fuzzy inference system approaching 1. So as the order of the fractional fuzzy inference system approach 1, its output approach the output of the a typical FIS. Here we consider the Mamdani FIS. Here this is the output of the Mamdani FIS, and these are the output of the some modes of FFIS. If we applied the FFIS on the inverted pendulum system, so as we said and predicted, we got more satisfactory results. And also we applied a Mackey-Gallas chaotic time series for the predictions purpose, and it turns out that by FFIS the accuracy increases. And actually, since fuzzy sets are a generalization of crisp sets, so if an AI system is equipped with a fuzzy systems, so its intelligence increases. Analogously, actually, if an AI system is equipped with fractional fuzzy inference system, the intelligence of AI system is also increases. A package has been prepared in order to implementing FFIS in MATLAB software very easily, and it is very simple. This package is accessible freely from the Masswork website, or can be found in the ResearchGate website. The package includes 4 files: the help, the main function, the example file, and its corresponding FIS file. And if someone, if this is this MATLAB code can be converted to the other languages if someone would like to use in the other languages. Finally, if we compare very briefly the FFIS with the typical fuzzy inference systems, you can say that the exploitation of information in FFIS is based on value and volume, but in typical fuzzy inference system only based on the value. The range of order in FFIS is the interval 0 and 1, but the typical fuzzy inference systems are first order, and FFIS are from multi-mode, and the design degree of freedom in FFIS is higher than typical FIS. And actually, you can easily replace a typical FIS with its corresponding FFIS in the application you have used a typical FIS, or in your new application. And indeed, by the use of FFIS, you obtain more satisfactory results. So for any question, please feel free to contact me through the email. Oh, I almost forgot to mention the last point. Do you remember the problem of Mr. and Mrs. Smith? Actually, thanks to the organizer of the seminar, they agreed to look at the world based on a new lens, which is in fact a fractional fuzzy lens. They now have a very good relationship, and more important than that, they now have 2 children. So based on this result, even if someone ignores undeniable effectiveness and importance of fractional fuzzy inference systems, he agrees that FFISs at least help us to fall in love and save the life. Thank you for your attention.